Hi.
Good evening, ma'am.
Hi, good evening. Was there a problem last week? Like, I couldn't find anyone actually last week.
Yeah, I tried to connect it, but
Oh,
unfortunately, due to low network signal, it's continuously disconnecting. That's why I can't able to again rejoin it because of low charging and also low signals in my area. There is a signal problem due to rain. That's why
okay.
I can't able to join it.
It's fine.
Yeah, ma'am.
And then, are you able to listen to my voice properly?
What? Yeah, I can. Complete some of the questions for assignments, but the some of things what I submitted is getting mistakes only.
Oh, okay. Do you want to discuss those problems first?
Yeah, we will
Uh,
see, ma'am.
by
If
the
you
way,
are
are you able to listen to my voice fine?
what, ma'am?
Are you able to listen to my voice?
Yeah, yeah. Is this audible only?
There is no problem, right?
Ah, yeah.
Fine. You can tell what are the problems you had. We can discuss that.
Wait a minute. I will. We see
You
the
can share the
assignment of.
screen by the way, if you want, or you can
Ah,
show using your phone. Any problem, anything is fine.
any individual topics, huh?
Okay.
Wait a minute. The thing is, shall we discuss about the direct assignment questions, ma'am, or you are saying any individual topics?
No, we can discuss the problems you guys
Assignment.
have first. We can discuss first.
Okay, that questions what in this assignment topic, right?
Right now I am teaching the week 3 one, not the I did not go week 5 until week 5.
Okay. Oh, some of them will come.
Huh. Yeah, until now I've gone through only till week 3, and then I'm supposed to discuss only the assignments which are already completed.
Okay. Okay, ma'am. Then fine.
Uh, you were asking about EBSD, right?
Yes.
So today I was planning to discuss the EBSD only actually.
That what recent assignment is HAT,
I cannot hear you
ions
properly actually.
microscope. You didn't get clear voice, right? Wait.
No, no, I couldn't hear the voice properly.
Uh,
Hello? 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 Uh,
Hello?
hello? You had a question, right, sir?
What you are going to discuss on today?
Today I
EB,
am
elect,
discussing how the sample is done. Sample preparation last class I discussed. This now I am discussing how the EDX and then EBSD results will look like.
okay, okay, ma'am, okay, ma'am.
Okay, so should I get started?
Yeah, ma'am. Yes.
I just give me 1 minute. I'll just leave. I'm not able to switch on the camera in this. I don't know why.
Ah, okay, ma'am.
I was supposed to show in this only. If I'm able to present, I'm not able to open. Uh, so this is FEACM. We discussed until now. Sir, are you able to see the FEACM properly? Hello?
Yeah, ma'am. It's clear only. I can able to see.
Yes, sir. Okay. So just now I kept the sample. You know to prepare the sample, right? So like I have recorded in previous year class, week class, and I've kept
Okay.
two different samples until now, like martensite sample and then one normal iron, which are undergone compression test. I just wanted to show how the difference, varying in working distance and varying in voltage, how the sample will be having different imaging. So this is what I was wanted to discuss. Like if no one was attending, but then if you want to do EBSD, we can start with EBSD also, sir. What do you want, sir? Like we can start with anything. I don't have a problem with that.
No problem. We will wait for if anyone joining it. We
No, no, sir, it's
will.
okay. Like I will anyway discuss this again later on also. So we can
Okay.
start with the EBSD sample preparation also, and then we can keep the sample. Do you want to do EBSD or like anything else, sir?
No, ma'am. You can follow this EBSD only. I will
Yeah, you are
notify.
interested. I remember you were talking about you are interested in EBSD.
Ah, yes.
Sir, you know the sample preparation, sir, part or the
No, ma'am.
analysis part you
Just
want?
I analysis part. Is this sufficient for me? Because sample preparation, I read it only, but I don't have that much preparation experience.
So
Okay,
I'll
anyway,
start sample preparations with it.
sample preparation. Okay.
You tell me, sir. Like, you want it start with sample preparation, or like we will start with analysis only.
Analysis we can see, madam. If possible, we will see in sample preparation later.
Later, okay,
We
sir.
will
You're
switch it.
interested in this one, so we will go with that. That's okay, not a problem. Okay, I hope this is recording. Like, they want that recording to be done. Recording is happening. Okay. We are using, sir, till now, like 1 second, sir. I'll open. You're able to see, sir, properly.
Yes, madam. I can able to see.
Uh-huh. So I'll open magnesium only, sir. You are interested in magnesium, right?
Yes.
So we have Aztec software first. We will do the analysis. I mean, we will usually do in channel 5. But then Aztec software is the one which we uses along with Joel. We got Oxford University one, and then we do have Crystal also. But then we don't use it much. We like for us user friendly. It's channel 5 only software that you can get like for anyone, or you can even buy the license as well. So I'll first open the software. Like I'll show you how the data will be present first, and then we can even see. 1 second. Someone is there. Okay. I'm Mohammed. Um, so now I'll be opening recrystallized samples, sir. Like how the recrystallization is done. Mohammed, I'm discussing like how to do the EBSD analysis, how the steps and all is followed in IT Delhi. Like this is how we usually follow here. I think so. It's fine with you, right, Mohammed?
Yes, yes, yes.
So sir is interested in magnesium. Sir is also working in magnesium. I remember he mentioned last week. So I'll start with magnesium only, and then I have rolled different samples. Like so, I'll first open recrystallized sample. We can see how the recrystallization was happening with varying time. Okay. So this is 3 minutes recrystallized sample. So usually it will be in EDX and EBSD. We will be doing in the same software. Uh, Here you can see, right, like there is EDX option as well as EBSD option. Right now we are interested in EBSD, so we'll go to EBSD. And then usually in EBSD, like if there are any other phases present, then we have to choose those phases also. For now, like I'm choosing magnesium only because most of the sample it has magnesium phase, alpha phase, majority, and then the like you have to first choose that it is pre-tilted 70 degrees, and then you have to choose RDTD any direction. That depends upon how you are keeping the sample. You have to make sure that sample is like kept exactly. We have other options as well. Like I have rolled this sample. If extruded also, rolling direction will become ED direction. Or as-cast dendritic structure, if you want to see, or any other thing, then RD will be like you can consider as a dendritic growth region direction. And then later on, we have to scan. I have kept the sample like last time, like in EBSD I showed in previous one. This was complete analysis is done. I'm just showing an example. Uh, the sample preparation for EBSD is pretty tricky compared to any other sample because not even a small scratch should be present in the sample, and then else it will that will be identified, and then some strain will be present around that region. So we have to be very careful in sample preparation. What we are following here is we will be doing polishing up to 4000, and then in emery paper, and then we will go for cloth polishing, and in cloth polishing we use colloidal silica 0.05 micrometer size. And then later on we will be ultrasonicating properly, and then we will be later on we will go for electropolishing. So electropolishing, we use orthophosphoric acid and ethanol solution. If you guys are even interested, you can mail me directly. I'll give you the composition for magnesium electropolishing, and I'll even mention the parameters. What are the parameters that are required? So, and then later on, you will have to choose a mode. Which mode do you want? If you want to see the, if you just want to see the grain, how the grain structure and everything is present, then you have to go for only for seeing the grain size. Mode 4x4 is enough. If you want to see the fine features like contraction twinning or any other twinning, then you have to go for lower modes like 2x2 or 1x1. It depends upon your interest. So usually right now we are just trying to see the texture. I'm working on texture, so we will be just interested in seeing, understanding how the complete texture sample analysis is done. So I for that I want grains only, and even when you're doing grains are also EBSD for grains, you have to make sure that minimum 150 grains are coming inside the scan region, that is ASTM standards. So always keep in mind this point, like it should be minimum 150 grains should be there for finding out the texture or anything. And then the mode will be as I'm interested only in texture, so the grain size is fine. So if I'm interested in further like small features and all, then I go for lower mode. But then for the sake of grain size and all, like I just go for 4x4, and then it takes lesser time. If you go for lower modes, then the time required will be very high. And then we have to optimize a solver. Like here you have to choose at least couple of bands. I don't this one will be present if Kikuchi patterns will be present here. Now right now EBSD detector is not present. I showed in previous class how the EBSD detector and everything is present. And then we even saw the Kikuchi patterns, how the Kikuchi patterns were varying from point to point, and then how the analysis was carried on. I just had given the brief description. And then we have to optimize solver here, and then acquired data. Like I have acquired the data in such a way that like minimum 150 grains are like there present. And then I have so 500 cross 500. I know the grain size of my sample, and then how many grains will come approximately. So I've kept 500 cross 500, and then step size I've kept zero point 0.7. That like depending upon the time. So if you see 500, like you don't have to burden your machine also. That's why you have to see the step size. Like it should be like 3 hours, 4 hours. Scanning time will be actually too much. Like 3 hours enough. Like 3 hours and 3.5 hours, 4 hours, up to 4 hours we can do. But more than 4 hours, it will actually put a lot of strain in the on the machine. So what we do, we make sure that it doesn't go beyond 3.5 hours or 4 hours, maximum 4 hours. So if I put zero point 0.7 as a step size for 500 cross 500 size, then the duration is around 3.5 hours. This is fine. So, and then after that, you will get the final analysis like this. You can see, and then this will be further analyzed. Like as you can see, this is in um, Z direction, means it has been rolled in, this is a rolling direction. So all the grains you can see that are in green only. This will be further processed, and you can see that there are some black spots. These are like you know, Kikuchi pattern was not identifying there. So we have to clean all these results later on. The phase pay statistics, you can see that it is around 93% magnesium is there, and then 6% was not identified. I hope you guys can see properly, right?
Yes, ma'am.
Yes. Okay.
Yeah, we
So
can see.
so minimum for a deformed sample up to 70% is fine, but if it is not a deformed sample, minimum we should get is like minimum 70% indexing should happen. Zero solution shouldn't be more than 30% usually. If it is more than 30%, it's better to see whether the sample preparation is fine or not, and then like you have to see whether Kikuchi pattern which you have chosen is the correct Kikuchi pattern or any other phases are happening. Uh, So any other phases are happening, so you have to make a cry files for that particularly, like these are using a xyz parameters. You have to say that this is this phase, like if any other precipitates are forming or any intermetallics are forming, so you have to tell that. Those things you can get it only from doing the xrd analysis. You can get abc parameters and all, and or then you can even check it using the literature review. And as you can see that there was not properly indexed, so we have done different others also. Sometimes these can be scratches, so you have to repeat it again. That's the reason why it has been repeated 3 times. I hope you can see, right, these scratches.
Yeah.
Yeah, so this is because of sample is not prepared properly, or if anything, some problem will be there. So accordingly, yeah, then you have to prepare the sample properly, or make sure that these scratches doesn't come in your EBSD, in order to make sure that you can, what you can do is first is run a rough scan about like 10 minutes or so before keeping like 4 hours scan. You run rough scan, then you'll able to understand whether there are some scratches or not in the sample. Then you'll be able to judge, like if no scratches, that region is scratch free region, then go for like doing a proper scanning, like 3-4 hours scanning. So that is what I do every time. Like we will see that one, this is a fast scan. First fast scan will be done, and later on I'll do it for the slow scan. So this is how usually the software works. But then for analysis part, I'll go. Just give me a minute. Just 1 minute. I'll open the analysis software. I was not expecting like we will be discussing on EBSD, so I did not prepare. Like just give me 1 minute. But then I'm happy to discuss all these things. One minute. So I'll first show how the cleaning and everything is done in EBSD, and then we can see the difference between two different samples, like how one sample is different. Like, so I'll start from the beginning. Are you guys able to see the screen completely, right? Like it's not like it is not seen, right? Like I don't know, I'm not able to see actually how you guys
Yeah.
are able.
Yeah, I can
Yeah,
see.
it's fine. It's fine.
Should I join? So this one right now I'm showing one particular, like after saving here, after completing the scan here, what we have to do is export to channel 5, so that we will be able to open using channel 5 software, or we can open using Aztec or MTEX or many other softwares you guys will be using for sure. I'm pretty sure that you might have gone through once at least in EBSD analysis. So, like for that, CPR and CTF, yeah, CTF format should be present. So we can export using this software itself, and then we will be able to open this CTR form or CTF form in any other format, Aztec, MTech, any software in Channel 5, etc. Once the saving is done, we can browse where do we want to save exactly, and after that saving is done, we will be having the results like this in this format in channel 5 or CR CRC or CTF, this format. So right now I'm using Channel 5 software. That's why I'm opening this one. It will be different for different softwares. And we are comfortable using Channel 5. So we have to make our own profile. We can get whatever we want to see, like we want to see the Schmidt's factor or anything. Those things can be done. So after pressing OK, we have to drag this to Tango and Mambo and Salsa. These are different. We can explore one by one. So I'm trying to show you only the how the cleaning and grain size analysis and how the texture is present. I'm just trying to show this part only for now. 1 second, just give me 1 minute. Yeah. So once you open in Channel 5, you can actually see that there are many black there are many unindexed part, right? If you like, it will not be good to present it in this way in papers or anything. So we have to clean a bit. We have to clean in such a way that we are not missing out any features, like and we shouldn't add any features and all. Like, it shouldn't read wrongly. See, there is a green grains here. It shouldn't make any different grains here. So you have to clean in such a way. We have to be very careful while cleaning. We can even detect the grains like this also, but then, like, to present in paper and all, it will be better if we clean it in like bit better. So we have to perform noise reduction. First, don't try to extrapolate very high, like try to extrapolate less. Like, first try to wide the spikes, like it will remove whatever it has present unnecessary spikes. And then first you can extrapolate wide spikes, and then extrapolate and make the zero solution lower. But then it's showing that still 12% zero solution is present. So we will increase a bit and then extrapolate using white spikes first. Always try doing first white spikes and then extrapolate using zero solution. So now it is showing that it's still 6.9% zero solution is there. So we will go to a little bit higher. First extrapolate and then extrapolate zero solution, and it is showing around 0.31. So this much is approximately is fine only. So we can apply now, and then when you apply, you can see that you can see the grain structure and all so nicely, right? From before, the zero solution was very bad and it was like present everywhere. Now you can see the grains are nicely seen, and you can see most of the grains are red in color. It means that it is all oriented in one direction, right? And then if you want to remove this black also, we can perform like first extrapolate to higher and then extrapolate to zero. Like, we can perform any amount depending upon the interest, like on how much you are losing the value and all. So now you have no um, unidentified region. So some amount of grains are in different orientation. You can even get how the grain boundary or the subgrain boundaries, and then band contrast map and how it is present. If any twins are and all, if twins are anything or any is present. If you want, we can see the rolled sample where it will be having lot of twins. This is a recrystallized sample, and you can see the grains are up more than 150 grains, and then you can. Like, if you want, you can count also. It should be, but every time it should be more than 150 grains for sure. In this area, I'm getting like more than 150 grains, and then this we can perform like grain size analysis, detect the grains, and then statistics. So then it will be showing that what is the average grain size. This is average grain size, and how it is varying in X direction, how it is varying in that direction. All those things you can get. This is the one basic thing that you can get from grain EBSD, grain size analysis. That also, and then we can actually perform many other things also. We can find out how the Schmidt factor is varying, how the strain is. So you can see in this region, the few of the grains has more strain. This few of the grains has less strained region. So all this can be seen in EBSD, and land maps can be plotted using this. It will take some time for plotting land maps. So whatever you are interested, how the grain boundary is varying or how the misorientation is happening, all this you can see in using. All this you can see using EBSD analysis in channel 5 also. This is in RD direction. Z means previously we have seen, have seen here. When I describe the sample, this is X, Y, Z, and Z I have given RD direction. That's why IPFZ is in all red, means in rolling direction all the grains are oriented. It is a very strong texture sample. So if you want, do you have any doubts till now? No? And if you want to prepare any other maps based on your interest, you can create those maps also. You can go to edit and make a new map. Here you will be able to get band contrast, Euler maps and all, phase, how is the phase distribution is present. And then if you have different like if you have some recrystallized sample, then recrystallization factor or IPFZ and grain boundary or phase boundary, everything like broad, everything, like if anything you are interested in, Schmidt factor also, how the strain is distributed inside the sample, everything you can see. You can plot whatever you are interested in. So this is one way, and then I'll try to open. This is recrystallized sample at lower time. We will see how the recrystallized sample at higher time looks like. So the previous sample I showed was recrystallized for only couple of minutes. This is for 1 hour. So we will see how the grain size is distribution is present. As you can see, this is having a bigger grain. The previous grains you saw, right? It was smaller grains. You can perform noise cancellation again. And now you can see that the previous sample had smaller grains and this sample is having higher grain size. You are able to see the difference, right? Guys, am I audible or not? Sir, Shivanathan sir. Sir, am I audible or not? Hi, Ajit. So this is how the grain size will vary from with varying time. Ajit, hello. Please, someone confirm that I'm audible.
Yeah, sure.
Yeah, I'm audible, right?
Yes, yes.
Ajit, I was explaining till now like how the uh, EBSD structure will, how to do the analysis of EBSD. That is what sir was interested. I think so. He had some network issue or something like that's why he was not able to talk. That's what he said previously also. Mohammed, did you understand what I taught to you till now? Ajit, do you have anything particular interest you want me to discuss? Like I'm actually in FESM room. Once again, I'll show you. I'm actually in FESM room. Like if you want, we can discuss anything interested. They wanted me to discuss about EBSD, so I was discussing about EBSD until now. Do you have any doubts or anything, Ajit? Fine, I'll continue discussing it then. And in this sample, you can see that there are no grain twin boundaries or anything is present because completely recrystallized sample. This is like no um, boundaries or anything is present. Like one now we will see some rolled samples. Then you will be able to understand like what I was telling, like how the samples like it will have twins and all because in rolled samples once again. This one. Okay, I'll choose something. So I was explaining you would how the noise reduction is done. Do you want me to repeat, Ajit? Okay.
No, yeah, it's okay. Go ahead, please.
Okay. So here you can see that this is a rolled sample. Here this is also almost having a texture sample. Most of the grains are oriented in one direction only. And or because as you can see that all the grains are colored in one grain. If there is a variation in orientation, then the grain color will be different. And here you can see that this is a rolled sample, right? So here you can see that there are twin boundaries present, twins. And let's try to find some nice twin. If your research if your area of interest is to see the how the twin boundaries are present, like then you can go for like lower scan speed. See here you can see some amount of twins are present, and here also. So as I was telling, in a rolled sample or deformed sample, usually twins will be present, as you can all see here. But then when we saw here previously, the no amount of twins were present and grains were completely recrystallized, and then strain-free grains or twin-free grains were present. So sometimes what happens in magnesium, one of the problem with magnesium is that it will have. So this is all about difference between rolled sample as well as recrystallized or annealed sample. In magnesium, what happens when you are doing polishing? Like it will create polishing twin. So you have to be very careful for soft material. You have to polish very slowly. You shouldn't put much pressure and all. Yeah, and then you should keep on lubricating either with water or kerosene. Many people use ethanol also. So it depends upon the sample to sample, the sample preparation also. Like as sir also discussed, few of the sample preparation is always advised to do electropolishing before doing EBSD. Then what are the other things that you have to keep in mind? Make sure that you don't have any scratches on the sample. Try to remove all the scratches before cloth electropolishing, only in cloth polishing. And then so when you come to electropollution, one layer of the sample will be removed, so that and then try to ultrasonicate just after the electropollution is done. So EBSD sample preparation will be very tricky, but then you will get very nice results, and then you can get very good papers out of it also. So that is all about EBSD. We will now go to EDX. If Ajit, if you have anything, we can discuss it regarding that, or else I'll go according to my plan, like how I was thinking. If you have anything particularly, then we can discuss that. I have no problem in that. Ajit?
Yeah, yeah.
Hi. Where are you from, Ajit? This is the first time you attending, or you attended the first class also?
Actually, at present I am at Patiala now. So
Hi.
there is some yeah related to network also. So I think I was joining first time.
The first class you joined, right? Yeah, I remember.
Once I think we can't discuss some due to some reasons
Yeah, yeah.
earlier
I'm
in
not
early case.
able to record it. They want me to record it and upload it on YouTube and all.
Yes, yes,
So Ajit, you are also PhD first year, right? If I'm not wrong.
yes, yes, yes. Yeah.
So what is your research area?
Basically, it's energy materials, perovskites,
Which what? Pyroscale.
per, ferroelectric materials.
Okay, ferroelectric materials. Okay. So you are working on steel, right? Or you told
No, no,
last?
no, no.
No,
Steel, basically on ceramics.
ceramics. Ha.
Yeah, yeah.
So one of the
Special.
so like you'll be doing SEM only, right? You told that you'll be doing SEM only, not SIM, like not ion microscopy, electron microscopy only, right?
Yeah, SEM,
Huh.
and also EDX, EDS also,
EDS. So
and
I am doing EDS. So I'll do EDS then now, right now. You can see. In my previous lecture interaction class, I have discussed about like how plasma, like sputtering will be done on the sample. You have to do yours is ceramic, right? So you always do sputtering on the sample because
yeah,
it is not
on
conducting sample. Huh.
yeah, yeah,
So always do the sputtering first. Like if you are like try to do very in nanometer range, like very small, and then if it is still you are having a charging issue, then you can go for higher thickness depending upon the interest and all. But I think so they have optimized for you guys. So you will be doing gold sputtering or platinum sputtering?
yeah. Sometime gold, mainly gold, but
Mainly gold. So every time you keep the sample, like it will be wasted, right, for you later. You'll be using the same sample again.
I think it's just gold paste
Just got
after
wasted.
sputtering.
Yeah, I know that like even people will be doing here and then they will not do anything after that, after split and FACM is done. So when you have optimized the parameters, right, like how much voltage and all you have to keep for your sample?
Yes, yes. Sometimes it's depends on the sample because sometimes we are doing with polymers also and polymer composites. So
So is it
it's necessary to.
composites?
Yes, please. Pardon, please.
Yours is composites.
Yeah, polymer and ceramic.
So you're working on composites. So how much voltage do you keep then? Because it's a
It,
polymer and then ceramic embedded.
yeah, yearly I think 20 kV and for ceramic
Huh.
plus 30 yearly and
Mhm.
for polymer it's low.
What like one like 5 6 kV?
It's nearly actually not a 5 6 but it's between 6 to 10 12. It depends on the thickness also and something.
Oh, you keep till 10 kV. Nice. Because for magnesium sample only we do it
It
at 8
depends.
kV.
It depends, basically, but kind of a polymer basically we have used if it's a composite form or it's a pure polymer form.
Hmm.
Sometime less than 10, nearly 8 and 7, it's enough. But sometime when we mix some composites and then we need some little bit higher.
More. Okay, nice. Then like so yours is, for you this lectures are very important, no? Like you have to go through the lectures because this exactly what was sir was also discussing in one of the class. That if there are some composites present that are hard phase like that ceramics and all embedded in polymer, then you have to choose the voltage accordingly. So like it was there in week 3 lecture.
Yes, yes. Actually, I also parallel. There is a coursework also, so similar, similar, similar process. I think there is also a microscopy part, also 20 to 30% of coursework part.
Nice.
So Yes,
I,
both are parallel now.
for you, it is nicely. For you particularly, it is very important. This course, then. Yeah. So we will. You know how the sample preparation. I have discussed in previous one how sample preparation was done. So like, if now we will be discussing how the EDAX will be getting like. So you have done EDAX, right, Ajit?
Yeah, EDX. Yes, yes.
So do you want me to discuss anything particularly in EDAX?
EDX right, right now actually. Basically, WDS is, I think, more better than EDS.
Which one is more better?
WD.
WDS. Acha, we have EPMA actually here. We do have, but then we don't have EDAX. I mean WDS here, but I did work in EPMA. WDS, like I have results also, a couple of those results, but I'm sure. Sorry, I
Is
don't know. You
that
should have mentioned me in the
FP7?
first class. I would have discussed. I'll try to discuss in the next class then, if possible.
Okay. Yeah.
Oh, I don't. I asked you which was your area of interest. You did not tell anything. That's why it's some people asked me to discuss about EBSD, so I discussed about EBSD and how the analysis and all was carried out. And if you are interested in WDS, I'll try to pull a couple of uh, slides and all for regarding WDS. I have done EPMA, that is based on WDS only. So
Okay.
what you will be using for WDS? Which instrument will you be using?
FP7
Huh?
is, I think,
Which one? I think so
am
I'm not able to listen properly. You can chat if you want. Like,
actually, I think there is a shutdown in whole Punjab for net, especially. So with it's Wi-Fi of I think university, so it's sometimes fluctuating.
okay. So which one do you use for WDS? Which instrument do you use for WDS?
I think it's a built in FSM. It's I think when
FECM
purchasing,
only. Okay.
I think EDS and WDS, it's twice. I think
Which FECM has WDS along with EDAX?
yes, ma'am.
Which FECM has WDS?
That are it depends during purchasing the instrument what you
No,
need,
no.
and
I'm
you can.
asking which one. Which instrument are you using for WDS? Which type of detectors are you using? I meant that.
Actually,
Have you done WDS till now?
no, actually, I have not actually done that one. Yeah,
So
but
it will be yeah, yeah, that requires separate detectors only for
yeah,
WDS.
extra,
Uh,
yeah, extra part at
correct,
that. I think that's needed for that one.
correct.
Uh, yeah, especially
EPMA
for
they uh, so EPMA they highly use for WDS only. That you can actually resolve very well. Like even in industrial level also they use EPMA. Um, so I can discuss more about EPMA at least for 10 to 15 minutes next class. I'll put few slides for that. Okay. Okay. So now I'll continue the class. Whatever I was thinking of uh, telling, like one by one. Like if you So first I'll discuss now. Until now we have seen EBSD, how the EBSD was done. So how the EBSD was done, EBSD analysis, how everything was done. We can now discuss like one by one the questions sir has put in assignment. If you WDS, I'll be discussing in the next class. I'll try to put some slides regarding WDS, and we have EPMA also. I'll show you the EPMA results. How is the difference between WDS and EDX results? I'll try to put those slides in the next week class. And then anyway, this one is like not this assignment, so you guys have anyway completed by now, and we will just go through the assignments. Meanwhile, along with that, I'll be also showing how different imaging will be seen in live. We can see right now how with very different working distance and varying voltage and all, how you are going to affect. We can see it directly only here now. Coming back. I'm not able to change the slide. Okay, present this one. Are you able to see the presentation?
Yes.
Okay. You're not able to see me now, right? They want my video also to be recorded along with that, but I don't know if I'm able to, if I'm sharing this, I cannot actually share the video. If it is required, I'll switch the sharing mode. I think so. For now, we will stick to this only. Okay. So again, I'm just introducing myself. This is Rashi R. I'm doing PhD in IT Delhi in Material Science and Engineering Department. I'm working under Professor Jayant Jain sir. And as you all know that I'm a course TA for scanning electron ion probe microscopy and material characterization taught by Devabrata Pradhan sir from IIT Kharagpur. And then, as I just wanted to have a small recap. Until now, we have seen how the history of microscopy, magnification, resolution, and lens aberrations and etc. And we have also seen what are the SEM and its capability parts of SEM, and have discussed, shown, and everything in live, where and all electron guns and then objective and then condenser lenses are present, and what are its role. Also, we have discussed in previous classes. And then electron probe diameter versus like how the probe current will vary for electron beam, etc. All those things I have shown here also with one of the powder samples. I showed with varying probe current how the sample imaging quality will vary, and then even with varying working distance also we saw how the imaging quality was varying, and with varying the voltage, that is acceleration voltage also, we saw that there is a variation in image quality. And we have to optimize everything based on what are the features that we want to see, whether it is topographical or the like BAC mode, or depending upon all that, we have to optimize the current, voltage, and the working distance. And then electron beam specimen interaction and then signal generation. We have seen the different AC, AC1, AC2, AC3, and then BAC signals formation, and X-ray signals, Agur, and many other signals will be forming. But then what we are interested in, we will be putting the detectors based on our region of interest, our signal interest, and then we'll be understanding. For instance, if you want to see the fracture sample, you have to try doing it in SE mode, secondary electron mode. You cannot do. You can you cannot try to do in BSc mode for fracture sample or wave sample or corrosion samples. We will not be able to see anything more because usually it will be for corrosion sample, for instance, it will be corroded with, like, it will be forming some chlorides or hydrides or some oxides or etc. will be forming on the sample. Then it will be of no use if you try to do any in BSc mode. So you have to know which mode you want to use, whether it is BSc mode, SC mode, or whatever you want to see. Like, usually these two modes are majorly used. If you want to see the distribution, phase distribution of different elements in the sum matrix, then you have to go for BSc mode. And if you want to see the topographical images, like or fracture sample or corrosion sample, for that in that case you have to go for secondary imaging mode. So we have seen the detectors. Sir has explained in detail in his one of his lectures, and then how I have also shown you directly how the sample preparation was done for powder samples as well as for solid metal samples. I showed you the live lecture, and sir was also discussed in detail for different samples. And then for EBSD, I can give you an overview, or I can make a video once how the EBSD sample preparation was done. If anyone is interested, you can let me know. I can give you complete details also. And then what are the good, like, SEM images, how to take, and that we can only get to know by experience. We have to see first with varying current or voltage and brightness contrast, and even the working distance, and many more things will be important, like when you're trying to take a good SEM image. I have few couple of good SEM image that has been considered as an for calendar for Joel mission or Oxford or anything. The parameters that are important is very important, like depending upon the sample, what parameters we have to choose. Just now Ajit told that he has some ceramic embedded in polymer, so you have to be careful what are the parameters that you choose for doing the analysis. Then until now we saw that main important parameters to be considered while capturing SEM image is that acceleration voltage, whether you do it at 5 kV or 3 kV or 10 kV or 15 or 30, that depends upon what you want to see, whether it is topographical image or BAC image, etc. All those things. And the working distance, believe me or not, for working distance plays a very crucial role, especially when it comes to BSc mode image, that backscattered electron mode image, because for during that time the working distance I showed you previously, where how the BSc detectors will come and go, and we will see now also, like how the BSc detectors and then SC detector images will be different. And then one more thing I wanted to tell is for BSc mode image, even for secondary electron mode image, if you do it at higher working distance, it will work. But then for BSc mode image, the working distance should be very low to get very good image. So be careful when you're doing BSc mode. You will not get easily imaging that very easily, but then you have to be patient to get very good images. In EPMA, that is not the case. Like, you will get imaging very easily, but in FESM, some issue is there because of aperture or something. So when you are doing in BAC, make sure that the working distance is low. And then the lens current, that sir has discussed, and size of the objective aperture also sir has discussed in detail all these things. And then I just wanted to say, give a recap regarding this also, how the accelerating voltage, if it is low or high, how the image formation was different. And I even showed in previous class, while having low accelerating voltage and as well as high accelerating voltage, we could see that if we had low accelerating voltage, the resolution of the material was very low. And when the accelerating voltage was high, but not very high, like 30 kV and all, but that time there is a resolution, you were able to see nice image formation and all. But then, like, what happens, the specimen will start becoming degrading more and more, especially if it is polymer or anything. The specimen damage will be higher in case of high accelerating voltage. So you have to see what is your which sample is yours. So you have to choose the voltage depending on that. And if the accelerating voltage is low, then the specimen damage will not be that high. So image information you get from low accelerating voltage is, as it will not be interacting with more deeper the interaction volume for low accelerating voltage we have seen previously will be having low if the accelerating voltage is less, and then if the accelerating voltage is more, then the interaction volume will be also more. So if it is low interaction volume, then we will be getting only the surface feature, like it is around 50 nanometer or so. So then we will be getting the surface feature. If the interaction volume is higher, then the deeper sample, like you will be getting the features from deeper, then you will be getting more. So if you want to see only the surface information, then you have to go for low accelerating voltage. Sorry, low accelerating voltage. And then if you want to know see BSc or like see X-ray elemental mapping or WDS etc., then you have to go for high accelerating voltage. The contamination that is possible, as sir is also discussed, that it will be more contaminated, like in the case of it gets easily stuck, easy to see but easy to stick, like, and not easy to see but then occurs more. It might not be seen, but then the contamination will be very higher in case of high accelerating voltage. And charge up, and previously also I showed you in one of the image. Now when we were doing the imaging, I tried to put more accelerating voltage, and we could see that the charging up was very high in the case of high acceleration voltage. And we also saw that if the scan speed is low, like, then charging up issue was very high. And then if the scan speed was fast scan speed, then the charging issue was very low. So and in it is in contraction contrary to this one. If you want to see the surface feature, you have to go for low acceleration voltage, and if you want to see the elemental mapping or elemental, like, point analysis or anything, line analysis or X-ray, for you, if you want the emission of X-rays, then you have to go for high acceleration voltage. I hope this is clear. And what is the effect of accelerating voltage on, sorry, this is not accelerating voltage, I'm sorry, how the effect of working distance, and what are the parameters that are going to vary, like, with working distance, like this also sir has discussed, like with varying, having a short working distance, we can have an electron beam diameter smaller, but because when it is coming, when the electron, consider from condenser lens and objective lens, the electron beam is coming, and when it comes, it will be having more, it will the beam will be smaller at this working distance compared to that of, consider I have kept the sample here. Then the beam diameter forming here will be smaller, right, compared to here. Like if I keep the sample here, it will be anyway, no matter how high vacuum we keep, it will be having some diffraction and all possible, like these things will be happening. So if you keep the sample here, the beam diameter will be higher. So beam diameter will be larger if you keep the working distance long, and then beam diameter will be smaller if the working distance is less. So objective lens strength will be stronger if you have the lower working distance, and the weak, so the objective working distance strength at this point will be having more effect. Objective lens will be here at the end, and then comes the final lens, like final diameter of the beam will be happening here. So if you keep the sample here, then the effect of this objective lens on this will be higher, because it will be having strong effect. But then when you keep the sample here, if you keep the sample here, the effect and the objective lens at which it's having its effect will be weak. Even the focal length will be shorter here. The f is lower, at which you have to focus. Here the focal length will be higher. But then what happens if by having a low focal length, the depth of focus, the focus at which it can actually focus will be very having lower. If the, yeah, this is what I'm telling. it will be having a shallow depth. If it is shorter, then if it is working distance is long, the depth of field will be higher. You will be able to see the image at 30x if you keep the working distance as around 20 mm. And maybe you can start seeing from 100x if you keep the working distance as 10 mm, and then you cannot go lower than this 100x. And then if you want to go to lower and lower magnification, then you have to increase the working distance. The minimum magnification that it can do minimum will be 30x. So if you have a 2 or 3 mm, then the minimum magnification that you can do probably will be around 200x. So maximum we can go till 1 lakh and all. So 1 lakh x or 2 lakh x, so depending upon our interest, but minimum the depth of field and the in area how much you can focus will be varying, depends upon the working distance. Okay, so this is the effect of how the working distance are going to vary with varying short and long, how the focal length and everything is going to vary. So one of the first question in the assignment 3 is dash objective aperture and then dash working distance is preferred to obtain high resolution. And I'm hoping that everyone has solved this question. We know that the objective aperture should be having larger, and then working distance should be smaller for having high resolution, because you know that her resolution was directly proportional to the alpha, and then inversely proportional to the wavelength. So from that, wavelength doesn't work here, but then if you keep the working distance lower, then you'll be able to get smaller beam size. Then you'll be able to resolve better. The resolution can be higher, and then better if the size of the electron probe is lower. So as you can see that objective aperture should be larger and the working distance should be smaller. So larger objective aperture and the smaller working distance is preferred to obtain high resolution, as it allows to obtain small probe, correct, probe size, small electron probe size. Okay. If it is smaller, if it is 1 nanometer, we will be able to resolve one distance between 1 nanometer. If this probe itself is around 10 nanometer, then how you will be able to resolve better between two different lower you cannot have better resolution if the probe diameter is higher. So contamination on the sample surface will increase if there is, like, as we know, the sample surface previously also I mentioned many times that it should be having it should be kept in completely kept in 1 second.
Hello.
Hi. Hi, Ajit.
Yeah, it's okay. I think the slide was disappear right now.
Huh?
Uh,
As the slides disappeared. Okay. Uh, Ajit.
It's okay. I think I think it's complete now.
1 second. Like, can you 1 second? Now, can you see the slides, Ajit? I
Right.
don't know. I'm not able to. Okay. I think everything went. Now, are you able to see Ajit's slides?
Not
Hello?
yet.
Not
I
keys.
there is I think my side there is also some poor network issue.
No,
So
network is very good actually here. IT Delhi. 1 second. I don't know what was wrong.
from my side also na because I think yeah it's okay. No it's okay.
Now it is.
Yeah
I think so I have to go fast now. Huh.
yeah.
Yeah.
Actually, I have some weak network right now.
Okay. Okay.
Yeah.
Uh,
Yes.
yeah. So as I we will go to second question, and then I'll be showing few of the APT results also to you guys. Like that, I'll be showing at the end, like how the analysis and all is done. Like APT sir was discussing in the week 3, lecture 15, I guess, if I'm not wrong. In that he mentioned about APT. First, we will complete this assignment, and then we will come back to APT. I'll show you few interesting results, like how the APT results will be seen. So yes, contamination of the sample surface. Ajit, are you sure you want me to discuss assignment problems, or do you want me to discuss anything else?
It's okay. I think assignments, I've already visited those assignments earlier.
Hmm. So you can tell what do you want. We can discuss that first, actually.
Yeah. As per your convenience, it's not,
I
yeah.
Okay,
Yeah,
we
please.
can see the imaging part, like if you want, or it's fine
I
for me. Like anything is fine actually. Um, Fine. Then we will complete the assignments first. Then, uh, or else I can even show you the APT results right now if you want. Wait, I have the APT results. How it is done.
yes, I think, it's better
Huh.
images.
So can you see the APT analysis PPT?
No,
Okay, 1 second. I'll share again. Now, Ajit, now?
yes, visible now, right now.
Okay. So this we have done APT analysis in APT analysis in IIT Madras. We have one APT Leap 5000. We have carried out the analysis there. Like if anyone is interested in detail, I'll be showing in detail like how the analysis is done later stage. But then I'm just skipping all these things, and then I'm trying to show only the results part, how the results are seen, and then how the analysis, how you have to read the APT results, and what is the importance of this, like APT. This is all in analysis part. If anyone is interested, I'll show you the analysis part, but I'm pretty sure if no one interested, like everyone wants to see just the results, so I'm just showing the results now. So you can see that here in this, okay, why am I not able to write? Mm, okay, as you can see that there is a green and then there is a red color, right? Like each and every green atom, each and every green point corresponds to one single atom. This is the beauty of APT. You will not be able. There is no like resolution can be. You can actually see the between two different points, like two different atoms, like how the atom distribution is present. This one in this sample, like this is a magnesium rare earth element which has completely solutionized, and then we will you can see that each and every 1 second. Huh. So you can even see like this how the distribution is present in 3D image, where are the precipitates and all are present. You can zoom also completely, and then in APT software, and then you can see how the size of the precipitates are present from, and then what is the composition, exact composition of the precipitate, and everything, morphology of the precipitate, how it is varying in 3 dimensional. All these things can be seen in APD. So if anyone interested, more interested, like you can contact me. For now, I just wanted to show some cool thing for this lecture. So that's why I got these results. And here you can see that there are some precipitates, like red precipitates and the green precipitates happening in different regions, so it is not completely homogenized. So here also you can see. So the size of the precipitate here is very big, and then the distribution is not uniform. So compared to before one, so here you that is the beauty of APT that sir was discussing also before. That we can actually see between two different atoms, and the resolution is like you can see two different atoms. Like the resolution is only because of its own atoms only, like how it is been distributed in the sample, rather than having any. It doesn't depend upon the source and all. It directly depends upon its own atoms itself. And then you'll be able to see nicely how the distribution is present and how precipitates are forming, etc. All these things. So this is to show that the distribution is happening at one particular region. This is done at grain boundary. That's why in the center there is a region where there are no precipitates present at all. But then in some region the precipitates are very highly concentrated. So you can do this type of analysis and etc. Like whenever you are interested and all. Like this is one of the thing. Best thing that sir has just given introduction. This is APT analysis, atom probe tomography. Um, this has very high application in terms of like understanding the properties and all for in nanoscale, even in very which the things you are not even able to resolve in TM, you can easily get resolved in APT, and with this APT you will be able to see in 3 dimension also, and how the distribution is happening from one point to another, and how the precipitates are present, and all those things, what is the morphology and everything you will be able to see in the case of APT. So coming back to our assignments, our boring assignments. Did you understand, Ajit, APT? I hope you understood. Okay, stop sharing. I'll share the normal one only then. Entire. So I'll start with this now. We will see how the we will see how now we will be doing and two different material first, martensite and then normal iron steel, more normal steel, and then you can see the difference between, you can see the different structure of martensite and then steel. So first I'll keep the sample inside. I've shown how the sample preparation and all is done in previous class. I'm sorry. So this is the stuff. This is the sample holder I was telling. Like we were using this sample holder for EBSD, and this is the sample holder for doing ACM analysis. And then you have to tell the specimen offset. You have to give the specimen surface, like how much is the thickness of the sample. I measured the thickness of the sample. It was around 5 mm. Then the voltage and all, we will start with, previously we have seen in for powder samples, we started with lower voltage, and then we went up to 10 voltage, and then we saw how the voltage is with varying voltage the image quality was different. So first we will keep the working distance here you can see that working distance is there. So first we'll try to keep at 20 mm and see how the, as you can see, the sample is coming up first, and we will see how the image quality is present, And then we will reduce the working distance again, and we will try to understand how the image quality is present. And then we will start with 1 kV. Sorry, 1 kV, and then we will fix the probe current to like 5, and then we will see the difference. Okay. So at 20 working distance and at 1 kV, how is the imaging quality? We will first see, and we have to first switch on the beam. The switch beam. We have to switch on the beam, and then first try to go in LDF, and then we will try to see martensite first because it has very good laid structure and all. Once again, for finding the sample, let me keep it at 10 kV, and then we can vary probe current. This is martensite sample. Okay, now we can go to lower kV. And you can see this is what I was telling. Here you can see, right? It is at 60 magnification, 60x. Let's try to go to lower magnification. It will go up to 25x. It can further, if you try to reduce the magnification, it will not be able to capture. So at working distance 20 the minimum magnification you'll be able to see is 25. And then let's try putting it in near 10 working distance, and then you can see that uh, and here you can see that it became 60. So I'm not able to go any magnification lower than 60. So minimum magnification you will be getting at working distance of 10 will be 60x. So if you keep on reducing the working distance, the minimum magnification at which you can take the image will also keep on increasing. So the depth of field will be less with increasing the with reducing the working distance. First, let's go back to 20 mm. So here you can see that you can reduce till 25. And then always try to do auto contrast brightness ACB first. Okay, once again. And then put it in reduced image. And then try to focus the sample. You're not able to focus properly because we are having one voltage, and then the working distance is also higher, and then so you're not getting good image, so like you cannot focus well. And this sample is also having here is also a metal, and it is not like it has any polymer or anything present, so we are not able to focus properly at 1 kV. Let's see how we are able to focus at 5 kV. And let's do ACB, and some amount of cracks or something you are able to see, right? So nice, it's good. Something we are able to focus in 5 kV. Thus we will be able to see, as sir was telling before, like as we know that surface features, if you want to see, then we have to do it focusing at lower voltage. Try to, if you want to take the image at around 100x, try to focus at 1000x, and then you'll be getting a good image in 100. Okay, so I'm trying to take the image at the 100, so I'll try to focus at 1000x. Not still able to focus so well because the working distance is very high. So let's try reducing the working distance. So first we'll go to 10 mm. You can see that the working distance is the distance between this one and the sample. So we have reduced the working distance now, and let's see how it will be seen at, let's go to lower magnification and then try doing ACB and remove this one. Quick. Sorry. And try to focus here. And let's go to higher magnification. And then see, we are getting so nice image. Are able to see the features so nicely, right?
Yes.
So this is the difference between varying the working distance, and we can even go to higher magnification. Let's try going at higher magnification as well. It's around 6,000. Still we are able to focus well. Nicely. Nope, that's it. And then let's try increasing the probe current or reducing the probe current. What do you want to do? Like, and do you want to increase the voltage to around maybe 10 and see where how the first we will see how we will get the image. And then every time you do, you have to focus a bit. Every time you vary the voltage or anything, you have to focus a bit. Okay, once again. Yeah. Are you able to see any difference in 5 kV and 10 kV?
Yes, yes.
You are able to see, right? So even we are at 10,000x, like we are able to see the dots also very nicely. And let's like, let me just resolve a bit better. Focus a bit better. Okay. So you can tell me what do you want to do right now, dude? Like this is around 20x now, around 16x, 20x will go, and then we'll try to resolve at 20x. We'll try to resolve that small. It's around 30x. Yes, we are able to resolve fine. But then if you want to more better, then we will try to increase the voltage furthermore. Maybe 15 we will keep. We will see how the image will look like at 15. When you do change, so try to first focus at lower magnification and then go to higher magnification. So I'm trying to focus at lower first. So we are at 15x, and then let's try to go to higher now. 15 kV. Sorry. Second. Go a little bit away from. I don't see any difference. Like we have probably have to reduce the working distance. Or increase the current or anything. Ajay, do you want to do anything particularly? Do you want me to increase the current or something now? Or do you want me to further increase the acceleration voltage? Or reduce the working distance?
Is it metallic now?
Huh?
Sample is metal.
What, Ajit?
Yes. The specimen is metallic.
The specimen is metallic. 1 second. We can go to other specimen. We have other sample also. This is actually. This is a martensite. We have another sample which is steel. I've kept this steel. So steel you can, I think so should be. I wanted you to show like the different. This one is steel. Last time I showed the powder sample, so I wanted to show something different this time. We were doing metal sample, but then time was over, so I thought, sure, I'll do this time. So okay, this is steel sample. For focusing any sample, first try to keep it in reduced image, and then first go to SEM. LDF mode is usually used to find the sample, and we have to go back to SEM mode. And we have detectors also, LED detectors. See here. Right until now, I'm just using SEM scan secondary electron detector only. I did not go to backscatter detector still. And then I'm trying to focus this now. And then try using this fine one. Yeah. So the voltage is around 15 kV. Let's see how much we can focus. This is how I'll try to see if any features are there. We are not able to see topographical image much because like we if 1 second, the sample is not like doesn't have any fracture sample or any sharp objects like that. That's why we are not able to see much difference here, right? We will try doing it in BSC mode, and then we will see how the image will be seen now. I'll just try to focus this, and then we'll go to BSC mode. I'll keep the BSC detector later. So we are not able to see much difference here. Let's leave it up to here, and we will go to BSC detector now. Just remember how it is seen now at 500x, and we'll try to see the same sample at maybe around in BSC mode in 500x only. Let's keep the BSD detector for now. So until now it was in SE mode. So the BSC detector will be, you have to give a command here. And then you have to change the detectors to BEDC, and then LED will be 0, and then UAD will be B3. Like this will be different for different FECM samples. That's it. Yeah, let's try to focus now. I'll try my best. Like in BAC, it'll take some time every time to focus, but let's hope that we will get soon now. The working distance is around 10 mm. Let's keep the working distance lower. As I mentioned before, for BAC detector, the working distance should be less. So first, always do auto contrast and brightness, and then try to focus the sample. Okay. One second. Beam is on. I'm trying to focus a bit. Here now, till now I was using fine focusing. Focus it's written here, right? But then I'll try to focus using coarse focusing. This is for coarse focusing. Usually in BSc it'll take some time to focus. I'll just show you the direct BAC images. How the BAC images will look. This is SE image. I'll show some nice ones. Sorry. So this is in secondary electron mode. But the same image, if you try to take, I don't have this image. But the same image, if you try to take using BSC, see, this is how the BSC image will look like. The same image. You can see the dendritic structure, right? The segregation. So this bright region will be heavy element, and then the little bit darker region will be light element. This bright, you, sir has already explained that this bright will be because it will be having higher uh, uh, electrons emitting per unit area because of more collision is happening, interaction between electrons, as the higher atomic numbers will have higher electrons. High elastic collision will be happening. That's why it will be giving more signals per unit area compared to that of lower atomic number samples. And so I'll try to focus. See, this is how it will look like in BSC image, but then in SC image you'll not be able to see this nicely. But then you have to focus it with some patience and all in BSC mode. So that's it. That is how it will be present.
Okay, thank you.
Fine, Najit.
Thank you.
This one also you wanted, right? X-ray, the X-ray analysis I have, but then not this one. Wait one second. That's so we will see one example how the EDX results will be seen also. So, okay. This is how the EDX analysis will look like. So this is a BSC image, and sorry, this is a BSC or SC image. This they have taken at for 4000, around 4000 X, and then this is secondary electron, secondary image, and then when you do the complete like analysis, not point mapping, you will be able to see like this, like how much percentage of magnesium is present, and then how much percentage of other elements are also present. If there are any impurities, usually carbon is not considered because like it will be showing wrong results for carbon. So carbon is not advised to use it in EDAX samples. For you cannot even consider as an like for evaluation purpose. And then this was the image. We can see that this bright, there is some bright region and there is some dark light region. And to see that what is that bright region, we can see that this bright region is it was brighter because it was having higher atomic number, which is ER. ER is having atomic number of around 68, and then magnesium has 12. So that's why it was the whole matrix is magnesium, and then it was having a little bit less brighter compared to this one. So we can do even point analysis, one particular point or line scan. Like if you do the line mapping, line scan, you can see how the variation is present. See, magnesium is depleted in this region, and erbium is having higher concentration in that particular line scan. And then you can also see there are two peaks present because there are two precipitates present happening in that region. So line scan also can be done, and point scan you can also do. You can see here, you can do point scan, you can do mapping, and you can do line scan and optimizing, and many other things can be done using WDS, EDAX. Sorry, WDS I'll show next time with few samples. This is not a line scan. This is a mapping. This is area mapping. They call area mapping for this one. So this is a point scan. So if at all if I'm interested, what is the chemical composition of the sample at this point, and then at this point, and then at this point, and then at this point, different points, then you can do the point scan analysis, and then you'll be having for each and every point spectrum, you'll be having, see, there are different point spectrum, right? Like you can have the different composition, how much is erbium is present there. So the point spectrum 1 will come where, like spectrum 1 is exactly in here. Here is a spectrum 1, here is a spectrum 1 inside the bright phase. So in that bright phase, it is shown that rare earth element, which is heavy element, is higher. And then we can go to spectrum 2. The spectrum 2 will be around, we will see that spectrum, we will see how is spectrum 5. This is spectrum 5. And then how is spectrum 7 varying. So the chemical composition of spectrum 5 will be magnesium is more. That is in dark region, the magnesium is more, and bright region is erbium, which is heavy element, is more. And here you can confirm that like bright regions are enriched in rare earth, which is heavy element, because it is brighter, because it is more electrons or more signals are coming from that region. More signals are coming in this region compared to this region. Fine. And then we can even see like any point, like any small point, we are able to see, make a small point, because this is FESM. And then in FESM we can even find out exact point analysis, like 1 point analysis. So here you can even find out the smaller than this. If you increase the magnification, then you will be able to see you will be able to see the lower area region also. This is how it is present. So it's fine now.
Yeah, it's fine. Thank you. Great.
Okay, so this is it. What's the time? It's around for 7:48. I think so. Like it's this today was the best time compared to other. Every time I have to just discuss the assignment problems. You guys are already good in doing assignments. We want to solve something like real problems, and then discuss about how it is actually useful for our research rather than just discussing the assignments. So I hope this session was a little bit useful, and even I'm happy that I discussed EBSD DAX rather than just discussing assignments. I think so we can stop here now. Like this much is fine. My throat is also paining talking for 2 hours continuously. I'll try to put some slides for next class. Like I'll try to discuss WDAs, and then what are the database, how it is present, how it's varying different and all. Like WDAs is good only, but then it will take some more time slowly. The process is very slow. I have been doing in EPMA here compared to EDX. EDX is very fast, like especially the Joel one, the Oxford Aztec software. You'll get results very easy, and this is also FACM, and it's nice. So I think so we can stop here for now. 10 minutes, it's okay. If you have any doubts, you can ask. Huh? Hello?
Sorry. When we deals with the elements, those are very close to each other in periodic table basically. Then I think EDS have some issue, yeah, because I think peaks are mix each other.
Yes.
And
the intensity also sometimes increases, but the intensity will not be actually that high, correct?
yeah. So for that purpose, I think WDS is something I think is better, but it's some slow. Yeah.
Yeah, even though it is slow, for you it will be especially required probably WDS if you have to resolve properly. Even the alpha and K beta, those things also will not be able to resolve properly in the EDAX. In WDS, you can even resolve very finely, very nicely those peaks also. And then the concentration, you'll be getting very exact concentration, not like you'll not be having confused concentration or anything like that. So yes, WDS is far better. compared to EDAX. But then if you have any in my samples, magnesium and erbium are way too different. Like there one is very low and one is very high. So for me, EDAX will work. And then even carbon also you cannot identify in case of EDAX. So for those steel samples also you will be having a problem. That carbon problem will be there. So you have to always go for WDS. You cannot rely on carbon composition in EDAX. That is also one more thing. And hydrogen, I don't think so you can resolve even in EPM, but I'll check once whether you will be able to resolve. I don't know whether we will be able to resolve or not, but I'll check once in WDS. So we will discuss a bit more about WDS next week.
Yeah, great. Great discussion today. Thank you.
It was very nice talking to you too, Ajit. Like, let me know if we can post the questions also if you have anything. We can even discuss about the research topic or anything. So I always like to connect and also it's fine only. So thank you, Ajit. Have a good evening.
Yeah, great. Okay. So
I will have to stop recording one second. And saving this recording is very important actually.
okay. Yeah.